Okay, so last time, the last thing we did was to look at how we can identify application of a linear map to a vector with application of a matrix to a vector in a space k to the power of n. When we phrase this application of a linear map to an abstract vector in terms of coordinates. Let me maybe state it again in more clear terms what we have actually proved. Well, not proved, but rather shown, because it was not uh, intended to be a proof, but well, it was rigorous. Yeah, you could regard it as a proof, but let's just state this. I don't know. Let's call it technique. Well, technique. Let L from V to W be a linear map. Let dimension V equal n, dimension W equal m. So finite dimensional spaces, right? Let BV V1 to Vn, a basis with fixed order of the vectors for coordinate maps, be a basis of V, and BW be basis of W. That just means here the same stands, except for the thing that is explicitly written. So here stands the same, be a basis of W. Right. Station of mathematicians who are too lazy to write such things out. Right. Let's BV 5BW be corresponding coordinate maps and the following works as we have shown. For any vector V in V, we can compute the coordinates of its image under L in the following way. The coordinates of its image under L, which are coordinates in L of V, and of course I mean now coordinates with respect to our chosen fixed basis, VW, but of course we can choose any such basis, we just have to remain consistent in computation. So if we have chosen that basis, choose here the same basis, we can compute those coordinates of the image of V under the linear map L as we just write into the matrix the corresponding coordinate vectors of the basis vectors of W, right? So this is a column vector of these coordinates of W1, right? Sorry, that's nonsense, of course. We just write into this matrix the coordinates of images of these vectors, of the basis vectors, right? F2, VW, VI, and W, the images. So until the last coordinate vector written as column vector, every vector, right? L, V, N, which, and of course we multiply by the coordinate vector V, V, V of V. That is what we have shown last time. Right, and for those column vectors will of course like k m1 because they had like m entries corresponding to the m coordinates in the spaces, right? And we have n columns in total, so the matrix is k. Recall that VW are k vector spaces, so the matrix is k m n, which fits with that, which is k and 1. We can multiply it, and with that, the result is indeed k and 1. Alrighty. That's just great. So, given a linear map L, given two bases, we just have to know how these images are represented with respect to the basis of the target space, and we already can then compute any vector in the domain space its coordinates with respect to the basis of the target space. And I want to show you a short verification of that, which looks quite more nice. Right? You can see that this is just, if you like think about it as a vector, right? Then we multiply it by matrix, and I have told you last time. But we can write it explicitly like these are some lambdas, like lambda n, right? So you can see very clearly that it is indeed true. Yesterday we had more intuitive approach, but now a formal approach. You just multiply this matrix by this coordinate vector. And yesterday I told you that it is just like a scalar product as if those were scalar entries. You can just carry out the matrix multiplication, then you will see that it is indeed the case. Right? Now, 1 plus 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 lambda n n, and that is equal to I just use linearity of both of the maps, which is exactly W1 L, and we have the sum lambda I VI, which is exactly V. So indeed, we have that thing here. So if you like the abstract formalism more, well, then you are good to go here because in this is obvious, right? You can see it right here. This is equal to this. If you like to work with just compositions of maps, then you can just see that it works like that. But well, yesterday I just had to derive it myself, and I didn't come up with this derivation right away, so I used another one, right? And well, it was essentially this, only that we have written that in large and had some steps that we could have dropped, right? This is much neater. But well, I told you I'm doing here math spontaneously, so I'm trying to come up with things. And when I don't manage to come up with something in a nice way, well, then it's just how it goes. All right. So what do we have next? That was just a note. All right. Another thing we wanted to do was, oh well, maybe I should give you an example. I know that it is really easy, but well, let's see. The thing is, such examples are quite tedious usually, so I don't like them at all. If I would like to give you an example, then I would like to give you a decent one where you see how powerful the formalism is, and that would be really, really annoying. Well, I mean, I don't want to give you a map from R2 to R2 or from R3 to R3 because that would be just really boring, right? I want to give you a map from some abstract space to some abstract space, but the thing is, I would have to write it down, everything of it, and that's quite hassle. Well, what could we do about that? Well, the thing is, this technique is not difficult. I mean, this per se is not difficult. You just take this, you take two bases. If you know the bases already, then you have just to uh, okay, well, the problem is to come up with an example. I would actually to know that it is linear immediately, I would actually use this approach. And if I spontaneously use that approach, then we would have to determine a matrix which you have already seen as the matrix from which I have derived linear map on the contrary. And that wouldn't be nice, right? So, okay, and in our case, I would just go with some simple maps on R2, which is also not that nice. I mean, every k vector space, every k dimensional, every k vector space is kind of the same. If you have chosen bases, it's kind of the same as any other vector space. As any other vector space of is any other what I want to say type today. What I want to say, if we take any n-dimensional k vector space, then this n-dimensional k vector space is actually structurally the same as the space k to the power of n. That's why the examples that actually explicitly take column vectors to column vectors specifying linear map, well, they are enough, because in truth you are always working with exactly those things. But what I had in mind, an abstract example, would be, for example, mapping polynomials to numbers. Of course, polynomials themselves wouldn't be a finite dimensional vector space, as we have seen, or we have claimed at least, but it is easy to see, right? Oh, yes, we have seen that because we have given an infinite basis of that. Yeah, but we could restrict the space of polynomials to a certain subspace, like to restrict how far the powers of the polynomials are allowed to go, and that would give such a space, and that could be mapped to something. I mean, there could be a linear map on the space mapping it to something. But the thing is, to come up with such examples, to know that they are linear for sure, I would use such a matrix, okay, maybe let me try to do it. If it will become too boring for me, then I'll drop it, but I'll try to do it. Okay, let's example. That way you also know how one derives such exercises of this kind, determine a linear map. It's not like the one who devises the exercise would how you devise the exercises determine the metrics of a linear map with respect to basis so and so. No, it's not like someone who give such exercise had to derive his metrics themselves. No, they start with the metrics. So we kind of go both ways, but use U formalism, and then you can imagine, well, we could think that this matrix, we could forget that it was given, and we could just start with those inputs, and we could try to derive it. What I mean is the following. Consider the vector spaces. I'll just say the vector space. Why not? Vector space. V equal to span one x squared x to the power 3, which is a subspace of Rx. That spans are vector spaces. You can prove yourself that it is a subset of that. Wow, that's very easily proved. Right, okay. And well, consider also W equal to the same thing. Now, what would we do? Wow. Two. Okay, let's maybe try to. Oh, now 1 x squared x is, of course, a basis of V. Call it BV. And wow, a simple way to derive basis would be to multiply it by an invertible matrix, right? So what we would do, oh well, we need not even do that. We just take invertible matrix. The thing is, that would be 4, 4. Oh, just I'm trying to derive now another basis because we need another basis of that to have a meaningful task, right? We want to have a map with respect to two different bases in the end, and I'm trying to come up now with a basis, and for that it would suffice to just give some matrix that is certainly invertible. And well, I don't want to do the Laplace stuff and things like that. I want 4 by 4, it would be quite tedious. So let me take something that is trivially invertible, like you probably know already that invertibility just never mind. Okay, yeah, I know what I will take. Let me do something crazy. Pi here, I don't know, we could even take a parameter, but okay, let's not overdo it. By 6, 6, 8, and then 2. And I claim that so another basis of that would be okay. Well, yeah, no, that's too easy. That's too easy, I think. But what would I like to achieve actually? Well, that does not necessarily have to do with that there. I'm just trying to derive another basis, another interesting basis, so to speak. Well, let's do little more interesting stuff. Well, let's try to. Okay. Oh well. That is already not interesting at all. Okay. I don't like this example. It's too boring. Too boring. Let's try to do something that is more fun, maybe. Mm. One, 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 okay. That. Okay. Let's do that. Minus one, 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 and let's do that. Let's do one, four, three, one, minus one, uh, oh, where did I have one? Yeah, one, one. Okay, I think it will work. One. Okay, I think that will work. One, 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 one. Okay, that works. Minus one, minus one, one. Okay, that works. Well, then that let's let's do something even more crazy. Let's do that. Let's do here pi. Let's do here 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 0 here -1 0 here 1 here 1 here 3 here 4 here 4 here 3 here 2 here 0. All right, now I claim well, 4x plus 3x square x 4 plus 3x, okay, 1 plus x, okay, then 1 pi, okay, here I was here, and pi 4 plus 3x squared, okay, that was 1 and x squared, that was pi x squared, right? No, that was 1, right, that was 1, so that is now x, and we have pi x squared. Okay, that works. Wait, 1 plus x. Okay, there's something wrong. No, that's okay. No, something wrong. Yes. Yeah, okay. Let's say we have pi x squared plus 1. Okay, pi x squared plus 1 plus x to the power of 3 minus 1, minus x squared. That is, x is missing. No, x isn't missing anymore. That is 1, that is x squared. Right, here is x squared. Here is right. Here is x squared, here is x, right? Plus x. That is wrong. Alright. Minus x squared. And 2x squared. Right. What I claim, 2x squared, alright, 4 plus 3, alright, so we have to position x squared and x squared, okay, x squared, x, okay, x, 3, x squared, right. What I claim is that this is another basis of our set. That you don't need to know. That was just me playing around. Well, there's of course some meaning behind it, but well, we don't need to know for now. It will be no fun, right? Alright, a claim, and of course has same number of elements. Claim is another basis, another basis of V equal W. Right. And that is called, we call it VI.I. Right. Okay. Wait a minute. Well, all right. This is a basis. Or at least I claim that it is a basis, and you can check that. You know how it goes. Oh, or I guess you know how it goes. Well, how you prove that? You just first you have to use Gauss, and well, actually, maybe you noticed, but what I did was Gauss in reverse. So to prove linear independence of these vectors, you just have to do the steps that I did in reverse. And of course, you can go back in the video and you just see that it works via Gauss. So yeah, you arrive at the matrix where I started at the unity matrix, right? Right. And why it works, actually, why this way around and that way around works, that we will discuss afterwards. But for now, continue the example. And now, well, like I said, now I'd like you to determine the linear map. I'd like to make an exercise where you have to determine the representation of a linear map with respect to the spaces. Of course, I would not try to figure out, well, how do I map this? No, what I would do would be just, well, I would take a matrix. I would take a matrix myself, and now it can really be any matrix. There's no need for invertibility or anything. But of course, I won't think it's non-invertible on purpose, or I think I want. Yeah, all right. I'll just take any arbitrary matrix. Oh, let me write it clearly. Right, 1, 1, 1, 1. And I will just multiply those vectors by it, right? So to obtain the linear map, and that would mean now I have that matrix multiplication, like 4, 0, 0, 3. Because I have to keep it the same. Oh, let's compute that quickly. Oh, well. Oh, what would I actually like to do? Well, I kind of use already that knowledge about coordinate representation there, right? So I'd like to have the coordinates of the vector I compute in that basis. And that's what I would like you to compute afterwards. Imagine you are a student and then you would have to compute that, right? So what I do here is like, well, our linear map would map, this will be, well, matrix multiplication. I take this line with this line with this line with this line with this, where I multiply each entry with each entry, and I sum up, right? The matrix multiplication, the usual one. For a plus, well, okay, something like that, I can probably compute without writing it down explicitly, right? I hope I still can. So 4 plus 9 is of course 13. When 32 plus 21 is something like 53, like right, 52 plus 21. The weakness of all mathematicians with computations, right? 52 plus 21 is 53. I guess I'm right. Okay, you can check it. For 24, 28, right? Then 4, 3, 7. All right, and that thing is the supposed image. 13 plus 53x. And now you also see why not all tasks in linear algebra are that neat. Because most times instructors try to make it somewhat neat, but well, if it doesn't work, I mean, not all tasks that are given as homeworks. That's 28, right? All right, 28, 28x squared plus 7 x to the power of 3. Right, next, we take this matrix and multiply it by the next one. 1, 2, 4, 3, 8, 7, 6, 7, 1, 2, 4, 8, 1, 1, 1, 1 is now multiplied by 2x squared, which means, well, here we had like 1, 3, right? So 2x squared would be 0, 0, 0, 0, 2, 0. Well, and what would that give? Well, of course, just the third column multiplied by 2. Right, that is 8, 12, 8, 2. Most easy computations are most difficult for mathematicians. 8, 12, 8. So I check another time. 2. Right. And we have 8x plus 12. Well, what was that? It was, of course, not x. That was 13, simply. That was plus 53x. Right. And of course, here too, just 8 plus 12x plus 8 x squared plus 8 x to the power 3 plus 2 x to the power 3. Right, that's next one. And we have same matrix. Seven, 6, 7. So, if you forgot, I'm devising now a task that we'll have to solve. Or you will have to solve for practice. Well, no, I wanted to show you that, so I'll solve it. Well, 1, 1, 0, 1, 0 pi 1. 1, 0 pi 1. Is that right? Well, let's see. That was 4, 3, 1, 0 pi 1. Right. 1, 0 pi 1. Right. And that gives, well, 1, 3, 4, 4 plus 4 pi. Right, 4 plus 4 pi, right? And 15 plus 6 pi. And 9 plus 4 pi. And 1, 2 plus pi. Okay, that's not a nice 2. That's a 2. Right. And that gives 4 plus 4 pi plus 15 plus 6 pi x plus 9 plus pi x squared plus 2 plus pi x to the power 3. Oops. All right, the last one remains. 1, 2, 4, 3, 8, 7, 6, 7, 1, 2, 4, 8, 1, 1, 1, 1. Here and here. Well, 0, 1, minus 1, 0. 0, 1, minus 1, 0. So x minus x squared plus x minus x squared plus x. And this gives minus 2, 1, minus 2, 0, which gives minus 2 plus x minus 2x squared. Right. So, and now you might be presented with the following task. Well, we derived tasks. We derived student task. Given well, is given basis okay, given a basis minus 6 squared 6, we find an element BV of V equal, and this is just the definition, right? This is just what this space is. So this not necessarily have to do anything with above thing. You should think about oh, you see what I mean. This is just defined as the space. We can define it, right? This is vector space. This is defined. And those who give you the task could appear on a homework sheet. They just tell you, well, that's a basis of this space. Then you might want to check this, so maybe not, right? Oh, it's not difficult, as I said. It's just Gauss, which I did in reverse here. A linear map L from that V to that V is defined by well, how could that be defined? Why are we following? Well, actually, Okay. Hmm. Right. Is defined via. There it occurs to me that we didn't have an important note about how we can define linear maps. It's obvious, but I should state it explicitly, and I'll do it in a minute. But for now, just oblige me. Right. 1353x plus 28x squared plus 7x to the power 3. Here 2x squared plus 12x plus 8x squared plus 2x to the power 3. Well, here 1, 2, 5, 1. Pi x squared plus 1 plus x to the power 3 is mapped to 4 plus pi plus plus 15 plus 6 pi multiplied by x plus 9 plus 4 pi multiplied by x squared plus 2 plus pi multiplied by x to the power 3. And finally, minus x squared plus x minus x squared plus x minus x squared plus x is mapped, sorry. When we map an element to another element, the notation is like this. That will be the notation, it goes from there to there. It's clear what is meant, but it's better to keep it consistent. Minus 2x squared. Right, and then the thing is, why they suddenly say that defines a linear map, even though it's just 4 mappings? Well, the thing is, they claimed that this, what is mapped here and for which the images are given, is a basis. And here, just short remark, because it's very easy to see. Remark images of basis elements of a finite dimensional domain space, that is the space from where the linear map goes, determine the linear map completely. Proof. Well, proof is just by linearity. By the linearity of the map. So L of V. I don't write it formally because it's just too obvious. The basis is the VI's as usual. And that is the vector V, right? The vector V is given. Its representation is uniquely determined, as we have proved, which results because of linearity of L in that. So you take any vector and you only know these images. And you know that the map is linear. Of course, it is just assumed. Like the right, we consider linear maps. And then you automatically have that. Because these images are already determined as some WI's. Right, so for any vector that must hold, and then this image is completely determined by that, because the coordinates are uniquely determined by the coordinates are uniquely determined with respect to this given basis. So given coordinates, and so if a vector is given, then it has a unique representation, that is, these coordinates lambda are already known, or they are determined by the vector, and those things are not supposed to be known. Then the image is already known because everything in here is known, right? And uniquely determined for this vector. Alternative thing, which is more rigorous conceptually, suppose G, L, V, W above linear. I mean, that's an alternative idea how you can see that. But actually it's the same, but well, let's look at the more rigorous approach, because this is a little bit wishy-washy. It is not exactly clear what we mean that it is already known, determined. That's why let's see, rigorous approach, yeah, linear, we've given G VI equal LVI, of course, for all VI element some basis of W, some basis of V, a basis of V. Then G equal L, since for any V have a unique basis representation V is equal lambda I VI, of course from 1 to n, right? Just represented in these vectors. Normal linear representation with respect to the basis for some lambda 1, lambda n, element k, right? V k vector space, always kept in mind, right? So now then by linearity, L of V equal L of the sum lambda I VI is equal to just by linearity, right? L VI. But now this was equal to G of VI by assumption. Right. When you to prove that under this assumption, the maps give same images for all of the vectors, right? And this is just linearity G applied in reverse, but well, you should get used to such applications. We just get that this is G of V. Just apply these steps in reverse here. Here I have written it in all detail, right? G of V, which proves that the maps are equal because the map, because the rule of how the maps map is the same, and we go from same space to same space. So indeed, if we claim that it is the basis of V, then this map is exactly determined by these mappings, right? If it is a basis, then it suffices to specify the mappings, and that already determines the map. So we can say it is defined via that, right? Now, what is the task? Problem. Find the representation of this matrix with respect to the basis oh let's call that yes, we call it PV and the monomial basis. Okay, I'll give you this version with a monomial basis. Then it's straightforward, right? Then this task is straightforward, and then deriving this task, I had even more work than you have to do, because now just apply the procedure above, and that is what do we do? Well, we just look at that, and we see the only thing that we have to have is to determine the coordinate vectors of our images with respect to the basis they ask to be the basis of the target space, and now it's the monomial basis, so we just write those coordinates like that, right? Wait, that's right. Yes, that's right. Of this matrix, I don't mean this matrix, of this L. This determines linear map, right? This L. Find the matrix representation. So find the matrix representing it as application to coordinates, yielding the coordinates of the image with respect to the basis BV and with respect to the monomial basis. This, and how do we do that? Well, very simply. Such a representation is, by the way, usually written something like here's our map, right? And here's BV, the basis from which the basis of the space from which we go. Here it's same space, but it's this basis, from this basis we want to go, and we want to go into the monomial basis. Let's call it BM, and then if we want to go and represent our arguments in the basis BV and our normals, our images in the monomial basis, we just take the images and write them down into this, right? Right, we take the first one. And it will be 13. 13. And remember, well, I should probably write it down. Now our W is just V, and our VW is BM, as the task asks. So we just have to write BM of whatever. 13 plus 53. Well, it's lengthy to write, but yeah, let's write it like this. L of V1, right? But now V1 is given L of V2 became of course not L. Here we have coordinate vector site. We recall 5 p.m. L of V3. Here 5 p.m. L of V4. Right, and this is this matrix. And in our case, it's just, well, we take the images and we take their coordinates. And here it would be the coordinates of that first. So 13, 33, 22, 7. First column. 13, 33, 22, 7, or whatever. 33, 22, 7, 28, 7. Seven. Then we have the second one. 8, 12, 8, 2. 8, 12, 8, 2. And we have the third one, which is simply, okay, not simply, 8, 12, 8, 2, okay, 4 plus 4 pi, 15 plus 6 pi, 9 plus 4 pi, 2 plus pi. 4 plus 4 pi, 16 plus whatever. 16 plus 6 pi, 9 plus 4 pi plus 2 plus pi. Okay. 9 plus 4 pi. No. 9 plus 2 plus 5. 2 plus pi. 9 plus 4 pi. 16 plus 6 pi. Right? 4 plus pi, 16 plus 6 pi, 9 plus 4 pi, 2 plus pi. So 15 plus 6 pi, 4 plus 4 pi, 15 plus 6 pi, 9 plus 4 pi, 2 plus pi, 16 plus 15 plus 6 pi. Alright, so you see that requires to pay attention, but if you write it down on the paper, it's not that problematic. Right, and then you have finally minus 2, 1, minus 2. Right, minus 2, 1, minus 2. Right, minus 2, 1, minus 2. And that is your representation of this map. right? Again, what does that mean? Well, someone gives you a polynomial like x. So a polynomial from V, for example, this polynomial, right? P, and asks you to compute, well, what are the coordinates of uh, L of P in the standard basis. And you do what? Well, you compute first the coordinates, compute coordinates in the basis for which we have the mapping matrix, right? In the matrix BV, in the basis BV, in this funny or scary looking basis. How do you do that? Well, that's basically Gauss. I won't do that, of course. Not that. Not that nice. How you compute that? How do you do that? Well, basically you use Gauss, right? So you compare these coefficients plus x plus 1. These coefficients are, well, then you have to represent it by this basis, right? Then you have just the first basis vector in this PV, like some, and you have some coefficient by it, some A1, some A2, V2, some A3, V3, some A4, V4. As you recall, your V1 has some monomial representation, so it is itself some like above some V1. I didn't want to write the numbers, right? V1 plus V2x plus V3x2 plus V4. Oh, and here are the ones for V1, V4, x3, and this gives you this, you get here same with upper index 2, so our coefficient here, here, and then you put the terms with same power of x together, and you compare them with those terms, and you can remember the representation of the space R of x by sequences. That's why you compare terms of same power of x with terms of same power of x, and this gives you a linear system for coefficients, right? Because you would just have something like a1 multiplied by b11 plus a2 multiplied by b21 and so on, and this will give you equal to 1. Then you will have same here, same here, same here. And well, what is given are these coefficients, because these coefficients are just from here is just this just from here, from this basis, like, right? The b's are just this and a's are unknown, so you have simply this vector of a1s A's, right? A2 or 4. Here you have your matrix that arises in like the matrix, well, you will have that and that, right? And you will have that as sum, so you will have B1, 1, B1, 2, B1, 3, B1, 4. Here you will have B2, 1, B2, 2, B2, 3, B2, 4. Here you will have B3, 1, B3, 2, B3, 3, B3, 4, and here you will have B4, 1, B4, 2, B4, 3, B4, 4. So just compute it. The scalar multiplicators by same monomials and compared with the coefficient here, and here's the comparison. You will just have here for the first, that was for 1, right? Here would be B1, 2, here this coefficient, right? That would be then equal to 1. The comparison of coefficients by same powers. Here you would have 1, here you would have 1, here you would have 1. Then you would have determined those A's, and with those A's you would go here to this matrix, and you would apply this matrix to the A vector, and then you would have solved that task, right? Well, it might seem difficult, but now imagine you wouldn't know that you can compute this linear map, this matrix representation for this linear map in that way. And now imagine someone asks you then to determine coordinates of this under this map, which is now given in that fashion. In that standard basis, it would be horror, right? And now imagine you would have to determine this coordinates not in the standard basis. Oh, okay, not in the standard basis, we would have another matrix. So we could compute it, of course, but okay. Even in the standard basis already, if you just look at that and you just don't know how the matrix representation works, oh, then good luck determining that, right? But now we have very easily from this computed representation matrix. Well, we didn't actually compute that, we just wrote it down basically, right? And then we can very easily compute those coordinates. That's great, right? Right. That's totally great, totally amazing. All right. All right, all right, all right. Wow. What else should we do? Oh, I mean, immediately. We have to do a lot of things, but immediately, what is the most urgent? Ah, now I remembered. Right, right, right. Well, this is basically how it works. It was a rather simple example, and you have also seen behind the scenes how one kind of devises such tasks. And this behind the scenes has reminded me of some important theorems that are not difficult at all, but nonetheless they are important. right? And that we will do now, that will be namely, well, we'd like to know what isomorphisms are good for, and, well, in that regard, how generally linear independence of vectors behaves under linear maps, because this is an important question, right? With linear independent vectors, we have basis at least of their span, because their span will have the dimension that is equal to their number, right? I hope that's obvious. I hope that's obvious for you, that is. And obviously it will be the span, just by definition. So, and well, in that way, we could transition. If we found some relation of linear independence on two spaces, we could kind of transition linear independence. That's our wish. All right, now theorem given v1 vn. There's just v1 vn now, right? No basis, nothing for now. V is again, of course, K vector space given a linear map L, now from some W, first again, some vector space to V. And now, I don't exactly remember, but I hope that it's true. I guess that's true. We'll try to prove it. If not, then, well, it probably doesn't work. Or maybe I won't be able to find the proof it will. Though it works, could happen. I'm now kind of tired, even though it should be simple. Claim L minus 1 to L Vn are linearly independent. So the pre-images, oh well, we already have a problem because the pre-images would actually be sets in general. So we have to make them behave properly. Oh wait, I am not sure. Let's keep it like that. What I mean by those, you see, if we have a general linear map, and of course it could be that the pre-image of such V1 is a whole set, right? So it could be that this is not equal to 1. Or it could even be that this is even equal to 0 if the map is not surjective, and like this vector doesn't have any pre-image, and that could be even equal 0. All possible. So we do it differently. We rephrase, we claim, but let me keep that for now so that you see the difference, right? That is not necessarily 1, because we could have that to this we map multiple vectors, right? Just imagine the 0 map. Imagine the 0 map, it brings everything to 0. So the pre-image of 0 under the 0 map would be the whole space V, the whole space W in this case, right? Okay. Claim if x1 meant L minus 1 V1, and then of course element of W, because this is how pre-image is defined, right? If you don't recall, pre-image is just defined as the set of all x in W such that L of x is equal V1, right? All right, and that is xn. It's 1 million. And keep in mind, we don't have any assumption on W. Of course, it only matters what we have in V, because the number of the vectors under consideration already determined by what by the number we take in V. So it doesn't matter what dimension W has. Then x1, xn are linearly independent too. Independent as well. And now let me erase that, because that would mean sets are linearly independent. Kind of not making much sense here. Okay. All right. Let's see. Let's see how we prove that. Proof. Suppose I think that's very easy actually. That's just the linearity, and that the linear independence is actually defined in linear terms. So suppose x1, xn are not linearly independent. So we prove the contraposition, right? Are not linearly independent. And as you recall, then what is the negation of linear independence? Of course, and there are indeed lambda 1, lambda n, element k, not all 0, such that with some lambda I xi over I equal equal to 1 from I equal to 1 to n is indeed 0, even though not all lambdas are 0, right? Negation of linear independence. But then linearity have I actually assumed that we map? Yes, given a linear map, right? But then linearity of L implies, well, we just apply it on both sides, right? And you recall one of our very first results on linear maps was just that L of 0 was 0, right? L of 0. Okay. And then you apply linearity to obtain this here. And well, those will be images of those vectors v1 to vn, and so this is equal to vi, right? Just by definition of pre-image. So if xi is pre-image of vi, then the image of xi is vi, no matter how we choose our xi. If it is in the pre-image set, then this is just by the definition of pre-image. Right, we obtain this, and lambdas will kept the same the whole time, so we have actually contradiction to linear independence of VIs. So indeed, the pre-image operation works very nicely. The pre-image keeps linear independence. Right. What about images? We cannot have a result as nice. We cannot have a result just as nice for general maps. General linear maps. Just consider the zero map. Most simple counterexample to that. The zero map, as we had that a few moments ago, that maps everything to zero. Just consider the zero map, and you already see the images are linearly dependent. More linearly dependent you can't get. No matter what vectors you choose here, it's just the same vector, and on top of that, it's not just the same vector, it's the same vector that is the zero vector, right? More linearly dependent you simply can't get. So we can have that for general maps, and there are also a bunch of other examples. So the zero map is not special in that regard. This is just the simplest counterexample, right? And but get theorem if L. By the way, here yeah, that's right. But we get something nice if L is injective. Then have f of v1, L of v1 v1 L of vn are linearly dependent. If and only if v1 to vn are linearly dependent. So you see, here we already have in it the result from any linear map. That is just, this is a shortcut to write that those are in the images if and only if. This is, by the way, if and only if and only if mathematicians write it like that. If and only if. Right, are linearly dependent if and only if, well, we could say better we say linearly independent, because linear independence is more interesting. But it's same statement, right? Because it's if and only if we could take a negation, or we could take the statement itself as I want to have it, right? And then there is the previous statement. L is still L, of course, I mean, is an injective linear map, and since it is supposed to be linear, we already have the statement about preimages, which is here just because we say that we take the images, so it's kind of like, and those vectors are not specified, it is just specified that we take the images and we refer to the images, so those vectors are supposed to be some preimages, so we kind of circumvent the need to write that the R element of the preimages, because this property of taking the images, of talking about images, already implicitly specifies that those are some preimages, any preimages, right? And this is then if and only if, right? And also the issue that such a map is not necessarily surjective. So to some vectors we don't have preimages, right? But here we circumvent that in that you already talk about images, so we talk automatically about such vectors that are indeed images, right? All right. And the application of that is very simple. You just go into W, for example, and you take some vectors in it, and you see they are linearly independent. And for some L that you have chosen, you see also they have the images. And well, if an L is any linear map, then you have already the linear independence of your preimages, no matter how you choose them. That's also nice. And the other way around, if your L is also injective, you can then go into V, and then you can look, and you can find some linear independent vectors, and then you can transition this linear independence to your image space. Or you find such vectors, and then you find a linear map, and then you get some vectors in this space, and that you wanted to get linearly independent vectors by just choosing linearly independent vectors in your domain space, right? If you find such an injective map. But well, that we have yet to prove, and if it actually works, well, we have only to prove one direction. We assume L is injective, and we assume V1 N are linearly independent. Then I mean, that's the opposite direction, right? We are proving that. And assume L of V1, L of Vn, so the images are linear independent. Then obtain this linear combination is 0 for not all lambda I equal to 0. So amongst this lambda i's, we can choose lambda i's so that dou of m I equal to 0, but this linear combination is equal to 0. And with that, by linearity of L, right? Linearity applied in reverse, you recall, but it is equality, so there's no asymmetry in equality. Equality is just those things relate like that. Those are equal things, right? So doesn't matter. I apply it in reverse, so forward, what you are probably used to is applying forward. This is because you read from left to right, but you should actually read in both directions. So, no, okay. We had earlier L injective implies kernel of L is equal 0. And so this vector is in the kernel by definition of the kernel because it is mapped to 0. And so lambda I, VI, 0, which contradicts the linear independence of this independence of VIs. So, indeed, we have this nice possibility to translate linear independence. We have injective map to the images, and when we have any linear map and we have preimages of vectors, we can translate linear independence to preimages, and that is nice, right? In particular, corollary for a bijective linear map. Bijective linear map dependence in the domain is same as independence of corresponding elements in the image. And by same, we really mean we can go in both directions. Yes, clearly because we are bijective. And because of that, we can also go in both directions in sense of independence. But I mean, both directions, it can't be that preimages are not there or they are not unique. We have exactly one-to-one correspondence. And taking a bunch of linear independent vectors in one thing, we just get exactly the bunch of corresponding linearly independent, as we know now, vectors in the other thing, right? We can just go back and forth with linear independence how we like. Independence in the domain is same as independence of corresponding elements in the image. And now it's time to recall the isomorphisms, because I didn't tell you an important thing. Theorem, or not theorem actually, we have proved everything we had to. Remark, when two vector spaces D and W are isomorphic, and that is, it asked, there is an isomorphism, and an isomorphism was a bijective linear map, an isomorphism between them. So bijective linear maps between them. When there is such a linear map, then the spaces can be seen as behaving identically from the point of view of linear algebra. That is, by isomorphic spaces, you can just always take the suitable copy and you can translate all the results via isomorphisms. Of course, because as you recall, linear maps preserve your scalar multiplication and they preserve your addition, right? And now this map is even bijective. So this is mapped to some W1. This is mapped to some W2. And if you go back, and this is mapped to some W3, but this W3 is exactly W1 plus W2. And this is really one-to-one. So basically computing in one space could have been done in other space and then go back without any alterations at all. So the structure is exactly the same. And same with scalar multiplication. And now we have also seen that we think with linear independence, and that is all bases are the same up to the formal distinction in which space we work. So from the point of view of linear algebra, all the properties just carry over, and every manipulation that we could have done in one space, we could have done in another space, obtaining exactly same corresponding elements after doing this manipulation, right? So the spaces are same from the point of view of linear algebra. And here you can experience that mathematics is sometimes not exactly precise because we do not specify exactly what that means that they are the same. That just is intuitively understood when we encounter something that results from this isomorphic relations, from this identification plus linearity, then we just understand automatically that same things happen. Of course, we could have written that down very rigorously, but usually it's not done. It's just understood by mathematicians when, so to speak, same things up to isomorphy happen, and that it happens in all considerations of linear algebra when we consider things on two isomorphic spaces is uh, just intuitive knowledge, right? So it is precise in the sense that we could write it down in every case when we use that, but well, after some time, it's not done anymore because it is clearer when we could write things down properly, right? And so it would just consume time if we really did. So we don't do it because we could do it anyway. All right? All right. Well, we are proceeding quite nicely. Okay, now I'd like to show you an interesting theorem. We had that linear map is completely determined. A linear map is completely determined by the images of some vectors in some basis, right? That was where was it actually? Right. That was here, right? images of basis elements of a finite dimension domain space determine the linear map completely. So it suffices to know the images of the basis elements of a given space, basis of the domain, and the map is already determined. But there is some converse statement. So, theorem. Which is quite nice when we have to know something about existence of linear maps. Theorem. A converse statement to linear map to given linear map being determined by images of basis vectors of a basis of the domain space. Right. What's the converse statement? Given finite, actually not even finite dimensional, as you can see, we do not assume anything about image space. So given finite dimensional space V and any vector space, and recall again, all spaces are K spaces with same field K. Finite dimensional space V, and I mean vector space, of course, but it's clear that I mean vector space, right? What else could I mean? And any vector space W, so we do not assume anything about dimension. Right. Given BV equal E1 to Vn basis of V, so the dimension of V is automatically n, if I assume that it is a basis, right? Number of vectors is the dimension, the number of vectors in the basis is the dimension, right? Given W1, Wn, not a basis, just any vectors in W, we just take any vectors. There exists a linear map mapping VI to WI for I from 1 to n, right? And this already determines the linear map, so it really says that the map exists because we can just define the map by linear extension. If we have defined this, like imagine we have defined that, and by linear extension means L of V, and now it is a definition, right? The map is only defined for that, right? But we can guess that it can be already defined because the map is determined by the images, and well, of course, this has some representation because the eyes are bases. That property does not disappear anywhere, right? We just define that to be that with those images that are supposed to be given. right? And this is the only way we could define this map, right? If there exists a linear map mapping that to that, then this linear map must be this map, because the map is already determined by the images, so we are defining that in a way like we must define it. But we don't know if it exists, right? Wow. Actually, in this case, and this is not at all common in mathematics, in this case, this is already the existence. For existence, and what do I mean by exist? Well, I could say that there exists a linear map on R that maps, I don't know, 3 to 9 and maps 4 to 16 and maps, I don't know, 1 to 1, and you see what I'm getting at? That could be a square polynomial, could be something else, could be just a function going through those points, right? But the point is, if I'm just claiming that something maps to something, it does not mean that it does exist. Even if it is determined by something, well, you have to show that it does exist, because you could assert some properties and claim that there exists an object that already has certain properties with those additional properties, and it need not exist at all. For example, I could say there exist crocodiles, and then I could say, well, there exist blue crocodiles, right? Same in mathematics. If you say that something exists, then you actually have to show proof. And in mathematics, it's even more rigorous. You have to show real proof. But I could really say there exists a linear map on R that maps this to this. Oh, by the way, if you do not notice, here this does not apply at all, because the basis of R is a field. So a basis of R is 1, and well, it is one-dimensional because it is already a basis, so the dimension is 1. So any basis would be 1, and 1, then this just doesn't work, right? Because I'm specifying for 3 things, so it's not this case. But I'm just saying I could claim about anything that it exists, that something with some properties exists. It need not exist at all. It could be that what does not exist mean? Well, it means that its existence within mathematics would be contradictory, or, well, uh, it's a philosophical question what non-existence in mathematics means, but clearly there's no linear map mapping this to this, because this relation is not linear at all. We could show directly that there can't be a linear map, and that would be shown that there is no linear map with this mapping properties on R to R. That would be shown just there would arise a contradiction. That is how you would show that. So mathematical non-existence actually means it would lead to a contradiction. But, well, it is our way to see that something does not exist in mathematics. What it actually means, mathematical non-existence, that we don't know. No one knows. But our way to see that something does not exist, and when we say that something does not exist, well, either it's obvious, or if we want to show that, well, we show the contradiction, right? But well, the interesting tasks, non-existence tasks that something does not exist can also be interesting. But, well, one of the types of interesting tasks is to show that something exists, and you have seen it is necessary, right? Right, and here we have even more abstract thing. Of course, we might already think, oh, it exists, but if we have not shown a proof, then we have a problem with mathematics. We can't just claim something exists because it seems to be plausible. And there are those things about which people claimed that it does not exist, for example, but it turned out to be existing. And the other way around. So it's not just some obsolete consideration. Right, for existence, just show that the map so that's our proof of existence. Right, just show that the map the and if we have this representation, this is exactly the coordinate representation because such a representation is unique. So it is unique and it is the coordinate representation. So if I have written down v element v in that way, then it is already the coordinate representation because it is the only way to write it. The only way to write it like this as linear combination of basis vectors is the coordinate representation, right? So I can write the map definition now VI, and now it is the definition because only L of VI's are defined. Oh, I mean, okay, it's not L of VI yet. I have to define this map as something, right? The map is not there yet. We are here. This was just intermezzo, right? I define this map like this. Just show that we map this is linear. So we just define L in that fashion from V to W is linear. And if we have shown this map, we can define, there's no problem. What is defining a map? That is defining a rule. And if we have such a V in V, for each V, we have to define exactly where it maps to. And well, we have such V in the vector space V. And it has such unique representation. We just can compute this representation. It is unique. Then we take this representation of V, and then we map then this V, knowing the representation that is unique, so it is proper. We map V to this using those representation coordinates, right? We can define such a map. And if we have shown that it is linear, we can define such a map. So such a map exists, and now it is linear. So there exists a linear map that indeed maps VI to WI because the representation of VI, recall that, was just 1 by VI, everything 0. And so this would be 1 by WI, other lambdas 0. Right, that is the only thing to show, and this is very easy, of course, is linear. So show that, so show that we get for the element V that okay, let's call that V tilde, call that V, and for lambda element K, what we have to show, well, that is our definition of L. We just apply the definition. We have to show the usual linearity property, and I have shown you how we can show that easily, right? It was in the lectures before. Well, We just apply that, and this is the coordinates of that. Well, if the coordinate representation of V is just oh, it has unique coordinate representation, and let's take this coordinate representation to look like this. So like this. Let's call the coefficients of the coordinate representation respectively lambda I and lambda tilde, and well, that is just lambda, right? Then this vector, if we already put it inside, right, and we get that, and then we apply the map. Well, not yet. We have those coordinates, and then take the sum together and get the coordinate representation of that vector, and that coordinate representation is just, well, you see, just component-wise, right? Sums, we get the coordinate representation in lambda I plus lambda I tilde, and we applied the map. After that, after getting this coordinate representation, we applied this map is defined here, which catapults those coordinates exactly at the places by wi, and this gives us, well, just this is simply even simpler. This is our game on vector spaces, right? And this is I and tilde wi, and this was just by definition, just look at L, that was lambda L, and look at the coordinate representation here of V, here already lambda taken in, but multiply by the inverse of lambda, and then you see it, right? Lambda L of V plus L of V tilde, which is exactly the linearity, right? So we have shown this map is linear. This map exists because we have just defined it properly, right? This here arise no problems by the definition of a map, because we have explicitly for each vector we have defined how this vector is mapped, and it gives a proper map. We can define it without problems. Now it is linear, so there exists a linear map with the desired property, and so it exists. Right. So that is quite interesting. So those vectors, wi's, they can be chosen in any way. And if we choose a basis on a domain space V, and this is any vector space W, no matter if finite dimension or whatever, and we choose some vectors in this space, no matter what vectors, it could be all zeros, it could be many of them zeros, it could be linearly dependent vectors, no matter what, it does not need to be a basis, nothing. It's just vectors, right? Everything works. Then we can have a linear map that maps those to those. Right, and this also is good for devising such tasks. Well, if one wants to have a pain while devising such tasks, because actually I could have literally taken a basis like this, and I could have written any polynomials there, and there would be a linear map mapping those to those, but I mean any polynomials up to degree 3 there, but well, I would have to find out myself what would be a map, and that wouldn't be that nice, as you can see here. That wouldn't be nice. Wouldn't want to solve this. Well, of course, this easy technical stuff, but wow, it would be such a pain. Right, that someone should do who has such homework. All right. All right. Wow. Today we had quite a wealth of results, actually. What is next? I think it's time for the dimension formula. And you have already seen one proof where I struggled. That will be probably the second one because, well, I don't know if I'll manage to prove that immediately. Because, yeah, there is a little bit to do, really. But let's say that and we'll try it. Theorem. Let L V to W be a linear map. Let dimension V be equal to n, so in particular it's finite. Then, by the way, I have stated dimension formula a little bit in less generality last time. We don't need any assumption on W. Now I recall after having done all those, right? Then we get the following formula. And this formula is really stunning, right? And it has a lot of applications in little stuff and in big stuff. But this formula is stunning because suddenly we get numbers in this abstract business. Of course, we had them in a way like in terms of dimensions, but now linear maps will connect those dimension numbers with each other in a certain way. Then we get the following formula. So for any linear map, we get this formula. And that will prove now, or I'll try. See if it works, right? And now you know what dimension is. Back then, it was not known at all, but now codimension of the kernel plus dimension of the image. Right. And some special cases, for example, if that is zero map, then clearly the dimension of the image is just zero. This is, by the way, the dimension of the zero space, that is just customarily zero. And the dimension of a kernel is the dimension of V, of course, because it is the whole V. Now, the other case, we have a bijective map. A bijective map, of course, by the way, no, that results from that. Okay, let's not take a bijective map. Let's take a map. Wow, I don't know. I have only the idea to take bijective map, but well, I don't want to spoil the fun. So let's just get into it. Right, we'll do it in a minute. So, well, what would we try to do? Well, we see it is out about dimensions. What connection do we have to dimensions of something tangible? Of course, it's basis. The basis we can play, as we have seen in the previous proof where I have struggled with things. Here we can play. So what would we try to do? Of course, try constructing try constructing basis of the kernel of L, image of L, extracting or taking such that it turns out that the numbers of vectors in the yield we claim. So if we take the basis of V, we take the basis of kernel L, and we take the basis of image L, then the number of vectors in basis of this plus the number of vectors in basis of this should be equal to the number of vectors in basis of this. Right? Yield we claim. How do we do that exactly? Maybe it's not the path to do it. It's just the thing that comes to my mind. This is the first thing you would think about, right? Because this is like not obvious thing, but maybe maybe we have to do it differently. I don't know. I don't know. Maybe we will even need theorems that I didn't prove. Oh, well, actually, each theorem could be proved, even starting with nothing. But maybe it will be too much of a task. I don't know. I don't know. I don't know anything. I'm just trying to prove that. Right. As I told you, I do not prepare things. I'm just trying to derive things myself. Oh, of course, I have had that stuff. Otherwise, I wouldn't even know the terms. But it was long ago, and now I'm really trying to derive the proofs myself. And you see if it works. Like the year above, it was pretty clear, right? It's so consistent, so beautiful. All right, what would we do now? If you would just take the basis, then you would not know anything about numbers, right? So let's try to do a different thing. We also haven't assumed anything about the map, right? But let's try to do the following. Let's. Yeah. I think that actually must work. If this claim is true, then that must work. Yes, that's very simple. That's actually very simple. I don't think it is proved like this, but yeah, it's very simple. Of P basis of kernel of L, let W. Wait. We don't know if this thing isn't actually infinite dimensional, but of course we know. If it is infinite dimensional, then the pre-images would yield infinitely many. I mean, would yield as many as we like linearly independent vectors according to our lemmas above, right? And that would just let the dimension of V explode. That's it, right? Because if we have the number of linear independent vectors larger than dimension of V, and already a number of dimension of V of those vectors give a basis, and then they give a span, and any of those vectors is spanned, and this is contradiction to linear independence. We had something similar in a proof. Well, I think previous lecture before previous. Right. All right. So this is finite, and so we can write pretty casually This is WL, B basis of image of L. Then, since that is a basis, no, since that is a basis, then L minus 1, W1, L minus 1, WL is linearly independent. We know it works for any map. We have for any linear map, so we have a buffer linear map. So that's linearly independent. Now, the thing is, now show V1, VK, L minus 1, W1, L minus 1, WL is linearly independent. Alright, does that show already we claim? No, it does not. Okay. Is linearly independent and spans V, and that spans is the verb. That means that the span of that is V. So it's like we, instead of writing span of this is V, we just name what it does, and it spans V, right? And spans V. Right. Right. First, linearly independent. So that would be a basis, right? That would be a basis, and this basis would consist exactly, and the number of vectors in the basis of V is unique, so that would be exactly the number of vectors in basis of V. That would be exactly 1 plus exactly k plus L, and that would be exactly dimension of kernel plus dimension of image, and that would be exactly dimension of V, because that is the basis of V. So the total number of vectors in here would be the dimension of V. Right, linear independence first. And keep in mind, if this is linear independent, this is linearly independent, it does not mean that that together is linearly independent. Very simple example, 1, 0, 0. A vector alone is linearly independent. We have that. And now 1, 0, 0. You could also replace it by 2 if you don't like it. This is again two vectors 1, 0, 0 and 0, 1, 0. This is linear independent, this is linear independent, taken together, of course, not linear independent, but you could replace it by 2 if you don't like that in this set we would only have 2 vectors because we don't have repetitions in the set. You could replace it by 2 and then you would have just that it doesn't work, right, without any problem that one of 3 vectors is actually the same. Right. Linear independence. Well, suppose they are not. So they are not linearly independent. Then that is let there be lambda 1 to lambda k, beta 1 to beta l, so that we sum gives 0. So lambda I plus beta I l 1 1. And this is just any pre-images, right? We just take any of the pre-images, right? We map is not necessarily injective, so we just take any element in here and we just denote it from now on like this, right? This is actually a set, but we just now fix an element in here and we denote this element by this, right? An element in the pre-image we fix, so an x such that L of x is W1, there could be another y such that this is true, but we fix with x and work with this x. Right. 0. Yeah. Just applying linearity of L, right? That is of course Wi where I is equal to 0. And well, so here it becomes interesting because I think this doesn't work that simply. So this really doesn't seem to work. Oh, interesting. Because if we take this equal to 0, then this is not necessarily linearly independent, right? So we can't just do that. We can't just do that. Because seemingly nothing prevents us from having this. Right? Those are not, well, well. Then we could replace those. Now we should show right, wait. Sorry. I have forgotten what that is. Remember that this is just element of the kernel of L for I. So that is actually 0. And by linear independence of this, we know that Wi is linearly independent because they were basis. You obtain that in such a choice, beta I is equal to 0 for I. I mean for I in here, or let's make J because that's better. For beta J, all beta J are 0. Because this is just 0 by kernel, so this is just 0, and this linear independence of this, so they are all 0, right? But if they are all 0, then we plug in is here, and this with this equality results in lambda I VI is equal to 0. And by linear independence of VI's, we get lambda I is equal to 0 for all I, right? So that is if we choose that to be this, okay, let's choose any lambda I, theta I, so that this is 0, and we have obtained and then all of the coefficients are already 0, which shows that the vectors are indeed linearly independent, right, by definition. Right, now show span of V1 to I don't even know anymore, VK? VK, right, VK. L minus 1, W1, L minus 1, WL is equal V. That is to show. Well, that's again quite easy. Let V element V, then yeah, good enough. Well, and we get what? Let's see. Wow. Then we get, well, okay, that's the basis of the image, right? Those W1 to WL, they'll be basis of image, and so L of V is equal to some lambda I. Wow, okay, I won't use the same. Of course, it's a different context, so you understand what we had above. We are already done with that, but okay, let me be rigorous for once. I mean, not it would be rigorous, but let me be accurate for once. WI for some WI and I, of course, from 1 to L. Some I in K. Remember, everything is K vector spaces. But that's by the way important. We should even state that in the demo. I mean, in the film. K vector spaces, so same field. That is important, of course. Vector spaces. Always, I think would work. Right, but this already very general. You can believe me. For and Well, then get V. So we get that V is actually mapped to this, right? So we get V is element of a preimage of that vector. Right. Okay. Okay. Let's. Okay. Hmm. Hmm. And we can't just conclude that this would be L minus 1 of this, because this is actually not necessarily an injective map, right? Yeah, of course, good. Okay, let me do the following. Let A1 and we don't know yet what dimension V has. I mean, we do not know nothing in dimension about dimension V in connection to the interesting dimensions. We only know dimension of V is n just by assumption. So we call the number that dimension of V is this is fine, and we call that in. So let this be basis, and I guess you can forget that. Let's carefully break it in for now. Be basis of V, then just like the proof. Um, um, Uniqueness of number of vectors in a basis Yeah, I have something in mind, but I'm not sure if I want to justify that properly or not. Yeah, you recall the replacement of vectors in a basis we did back then, right? There was like one coefficient in the representation of a vector we tried to smuggle in into the basis at the expense of taking out a vector of a basis. Uh, there was that one coefficient in the representation was not zero. Of course, it will be again the case here because O coefficient 0 would be a zero vector, and we could smuggle in one vector one by one. We could smuggle in all vectors because the vectors in question are linearly independent. So actually, the procedure we applied in that proof, it would work with any linearly independent vectors in the space. Because the only thing we needed was actually linear independence. We didn't need that it was that everything we smuggled in constitute a basis. We just needed that the thing we smuggled in was linearly independent. If you recall, it was all about um, in any iteration, some vector of the basis we smuggle into should have a non-zero coefficient, and that was only based on linear independence of the vectors in question and not on the basis property, right? You would like to look at that. It is possible. Just here. Where was that proof? Let's see. Hmm, hmm, hmm. I think it was here, right? I think it was here. Oh well. How long will it take? Okay, that's a little bit comfy. Field. Okay, so it was space. Well. Dimension of a vector space, alright. No, I think it was, no. Okay, that was the previous one. No, it was this one, I think. Right, you recall this procedure? We wanted to smuggle in this W, and we only needed some lambda I tilde, which was not zero in this representation. Right? And then we had that with signs here being not quite right? But it didn't change anything because it didn't change constants. And then we had that those were linearly independent, right? And we had that span. Right. And we have checked that, right? And we didn't need anything because it was just to check that this is span of this. And then we have that. And then we only had this, and we only had linear independence in the basis, right? So this procedure actually works for any insertion of a tuple of linear independent vectors instead of basis vectors. Right, now that this is justified, we iteratively proceed, and it is all the same, it works, alright. You can go through VI.I properly if you are uncertain about that. It works for sure. I mean, I have checked it now myself. Mhm. Oh, well, that takes time. Ha ha ha. Alright, where were we? Huh, looks neat, right? A lot. Set. Right. Right, we were here. Right. Maybe just like profession uniqueness just in the basis that we have just seen, we can obtain by replacement, and I just make the numbers just right. So it doesn't matter what the order is. I mean, for our argument, it doesn't matter. So I'll just make the order just to not have trouble writing down. And here we don't consider coordinates, so it doesn't matter what the order is. Only thing that matters is how those vectors function as a basis. Right? So not doing anything criminal. Is basis. All right. But this is really nice because that V1 to VK was the basis of the kernel. Then have V, we have V, our vector is equal to some, I don't know, GI, you know, doesn't matter what I call the constants, right? It only matters what role we play in what structures. A plus F J d tilde J. And now claim well, what do we claim? Um, right. We claim J tilde is element span L minus 1 W1 L minus 1 WL. Right. Well, F uh, J J is equal. I just brought this on the other side and I apply it out on both sides after bringing it on the other side. VI vectors equal to LV. You see, that is because that disappears because those vectors are in the kernel. That is why we brought them in. We have now a representation of that. Okay. Yeah, well, want to show something. Want to show something to have that these vectors, or that the images of these vectors are actually linearly independent. Show that span show that restriction of L into the span of a k plus 1 a children n, right? And restriction, that's just like restriction of the operations that we had when we talked about subspaces. And just restriction means it takes for that for the element this exactly L of this element, just the domain is different, the domain is not the span, and it goes, of course, restriction always does that. It goes on the span k1 n, and it goes in the W as injective. And for that have only to show by the criterion for the injectivity, right? Have only to show that whenever that show that always lambda k1 not k1 but j, where j goes from k1 to n, right? Lambda j with tilde, of course, with tilde j, and that's the sum. So any element in this span equals 0 implies that this element is already 0. Implies lambda j tilde j is 0. Right. This is what we have. And let's see that it is the case. Well, basically, it just follows by us having a basis of a kernel here. That is, the rest is certainly has nothing to do with kernel, but now showed rigorously. Um, I mean, that would already mean, because of linear independence, that all the coefficients are zero. We would have taken this vector. It would not mean that it is in the kernel, right? We just mean that the kernel is only the zero vector, right? How do we show that? Well, if L lambda j. So we have to show this implication, right? Because we have shown that kernel being equal to zero, and that is every vector that is mapped to zero is indeed the zero vector, is equivalent to L being injective, and we want now this restriction to be injective. We take some vector this restriction and have to show that whenever it is mapped to zero, it was already zero, right? Because zero, and we just use our basis of a kernel, and well, since that is basis of a kernel, we have, and that is element of a kernel, we have that thing for some my VI, right? That was the basis of a kernel for some my k on I, which is here from 1 to k, right? All right. But lambda j, ah, lambda j, VJ theorem minus my VI equals 0 gives a linear representation of 0. Hence, just because those vectors together with those vectors constitute the basis, recall they constitute the basis because, yeah, right, that is a basis, right, of 0. Linear representation of 0. Hence, obtain by linear independence, since we are basis, we are linear independent. The J together with ice that lambda J's and mice are all 0. So, in particular, lambda J's are 0, and this shows that this was indeed 0 as wished. So, that shows lambda J with J children is indeed 0 as wished. Again, indeed, L restriction to a k plus 1 children a and children is injective. Oh, but if it is injective, having injectivity, we know that these vectors are linearly independent. Having injectivity, we know that the images of these vectors are linearly independent. W k plus 1 to Wn is linearly the images of these vectors. Then of W k plus 1 until V tilde k plus 1 of V tilde n are linearly independent. They are also indeed a basis of image of L since for the representational basis lambda I VI V kernel part lambda J children V J children get L of V is equal L of lambda I VI equals 0 by definition of a kernel. That was the basis of the kernel, so each of these vectors in the kernel plus lambda J children J children, which shows that every vector in the image, so we have taken in V, we have applied out, obtained that we any possible vector of the image because V is chosen a better definition of the image, right? It shows image of L is equal to the span of VK plus 1 tilde till Vn tilde. Right, so we thought the proof is finished, but let me go through it another time because there was a lot of jumps, not gaps, but jumps. That thing. Wait a minute. I isn't it? Indeed. Mm-hmm. Indeed, that all. Really, that all. Was actually not needed. That was all not needed. We can take it into the brackets. That is all not needed. The proof starts there. And that was just how one could start to think about it. It didn't end successfully, but in the end it did. Right, but this base, no. Okay, we took a basis, right? U1 tilde to Vn tilde. We just took a basis with it, right? You can do that to find a dimensional space. Just like in the proof of uniqueness of numbers of vectors in a basis, we do this replacement procedure. We can obtain via replacement a basis, right? And here we had, okay, something we need. We need that piece. That piece we need indeed. We need that this is basis of a kernel. Right. Right. That piece we need. Other things we don't need. Right. All right. All right. Then we take a basis. We took a basis of a kernel. D1 to Vk. We know kernel is a subspace, and it is a finite dimensional subspace because our space is finite dimensional. We took a basis of a kernel. Then we took a basis, V1 tilde, V and tilde, a basis of V, and then we just placed, smuggled in the kernel vectors into it, on the cost of course, omitting some vectors in the spaces. And we have verified that it works. right? And we have written, and then what we wanted to show, that this basis actually allows us to have this basis of a kernel, which we already have, so that is true. And we wanted to have that uh, actually there is a basis of the image having exactly the number of vectors n minus k. And for that we have just shown that the images of this are a basis which has already exactly n minus k elements, and that vectors are really distinct vectors. Well, we have shown injectivity. Okay, and we needed linear independence, and we needed span to have that basis basis. That the images of these vectors are basis of image, right? And so we claimed what? I don't think we needed that. We really didn't need that either. Right, that was just my thinking. We just need to show that those vectors are indeed mapped to distinct things. And also, we need the injectivity, and we need injectivity also to translate linear independence. So we have shown injectivity on that. Right, here we have shown injectivity exactly by the choice of this basis with modeled in the kernel, and then we kind of used that this is what remains if we really remove the basis of a kernel from a basis. The vector that remained will kind of kernel free, kernel property free. So of course we would expect that a map restricted to them, map restricted to a span, is injective, because we kind of removed the kernelness in that we removed the kernel part of the basis, that we have derived the basis with explicit kernel part. Right. This gives value independence, right? And that shows this. So we had that this is injective, and then those are of course linearly independent, because we have an injective map from a vector space to another vector space W, and those and the images are the injective map of any linearly independent vectors. Linear independence is independent of whether we have I in a subspace or in a large vector space, right? This linear independent, and this is linear independent, and that this map is restricted to something, it does not affect linear independence in W. It is just existence of constants or non-existence of constants, so the linear relation holds. It does not matter that we obtained the images that way, right? It should be clear. There's just elements of W, so they satisfy linear independence relation not, and we do satisfy that, which we obtained via this restriction, having W as image of this map, and having this vectors being mapped by the injective map. Then, right? Okay. And here I need a basis, because we now have shown that they also span space, for which we have just taken any element of the image, because V was a arbitrary element, and we applied to arbitrary element, and we have shown that this is already represented by, sorry, this is of course by the images of these vectors. This is applied on both sides, right? And here I have of course to apply, and I have applied linearity, and here I have that this image is in the span of the images, which shows this, right? And with that we have that image of L has those vectors, sorry, of course image, but they are distinct, that we have also shown because it is injective, and then we have this number n minus k. We could just go through the vectors and just count them, right? And here we have a number k, so n minus k plus k is equal n, which is the number of the vectors in the basis of V, which shows the dimension formula. That shows the desired dimension formula. And I'd like to say that this dimension formula is used in a wealth of applications within mathematics and generally to obtain solutions of something, to establish bijectivity of maps and for whatnot. So it is really a great result, a milestone. It is really great. And next time we'll probably look at some corollaries of that, maybe also at some applications. It is really mighty, mighty stuff that helps for existence and helps for establishing of solutions, of systems, of integral equations, of differential equations, or mostly integral equations, but also differential equations. Right. Of course, simple linear equations. And also a great deal of theorems uses that. So it is really a milestone. It's a really important theorem. Everyone who thinks that they know linear algebra should know this formula. It is absolutely important. Right, I think that's it for now. We have done a lot today. Well, and enjoy the result. And you have really earned it to enjoy it. You have kept with me all this time. I mean, all this time of this session. That's a great achievement, I must say. Okay, thank you. Till the next time.